In this video, I will show you how to calculate the equivalent impedance of a circuit when the circuit is composed of a resistor, inductor and capacitors. Okay, see, find the equivalent impedance of the following circuit across the A and B terminals by considering omega, angular frequency omega equal to 10 radian per second. See, we have to find the equivalent impedance. At first you have to understand what is equivalent impedance. Equivalent impedance indicates an impedance which can replace this entire network, which can replace this big network with a single impedance, and that equivalent impedance will not change the value of total voltage and total current of this circuit. Okay, so when we will find the equivalent impedance, I can say that I can replace this entire network with that impedance. Okay, now see, here we have this resistor, inductor and capacitors. So at first you have to understand how do we solve this kind of circuit. I will use so-called point method. I will continue the points as long as I do not encounter any resistor, inductor or capacitor. See, this is our A point. I cannot go beyond this because here I will encounter this resistor. Or this is our point B. I cannot go beyond this because here I will encounter this resistor and the capacitor. So let's say this is our C point. After indicating C point C, I cannot go in this direction, this direction, this direction, this direction or this direction because I will encounter either resistor, capacitor or inductors. Okay, so let's say this is our D point C. I cannot continue the D points because in this direction I have inductor, in this direction I have this inductor and in this direction I have this capacitor. Okay, so let's say this is our E point C. I cannot go beyond this because resistor, capacitor. I indicate this node or junction with F. See, I cannot go in this direction because I have this 10 ohm resistor, in this direction because I have this 5 millifarad capacitor, and in this direction because I have this 50 ohm resistor. Okay, so these are the 6 points in our circuit. After that you have to indicate the branches of this circuit. So at first you have to understand what is branch in a circuit. The branch of a network is the path of current flow in which the current will remain same throughout that branch. Look at between A and C terminal. Let's say if I inject a current I here, you will see the current I will be same up to this C terminal. So I can say that I will get a branch between A and C terminals. Now see, when the current will get into this C point, it will have total 4 paths to divide. One is in this direction, another portion is in this direction, another portion is in this direction, another portion is in this direction. See, the current that will be outgoing from this C terminal will return to this F terminal through this 10 ohm resistor. The current outgoing in this direction will be incoming to this F terminal. So from C to F I will have total 2 different paths for current flow. So I will get total 2 branches from C to F. Okay, now see, the 2 currents will get combined at F point and that will be outgoing from this F point and that will be entering at this E point. So I can say that from F to E I will get a branch. Now look at this C terminal. This current is outgoing and that will be entering at this E terminal. So I will get another branch from this C to E terminal. Now these 2 currents will get combined and I will get an outgoing current towards this D terminal. So I can say that from D to E I will get another branch. Now see, I will get a current that is outgoing from this C terminal towards this D terminal. I will get a branch between C and D terminal. Now see, the current, this current and this current will get combined and that will be outgoing from this D terminal towards this B terminal. So I can say that I will have another branch from D to B. Now let me calculate the total branches of this network. 1, 3, 4, 5, 6, 7, 8. So here I will get total 8 branches. Okay, in the next circuit I will replace all these resistor, inductor or capacitors with their equivalent branch impedances. Now let's say the branch between A and C point, it has an impedance of Z1. The branch between this B2D terminal, let's say that has a branch impedance of Z2. The branch between this C2D terminal has branch impedance of Z3. The branch between this C2 F terminal consists of 10 ohm resistor, has branch impedance of Z4, and this branch has a branch impedance of Z5. The branch between C2 E terminal has a branch impedance of Z6. The branch impedance between this D2 E terminal has a let's say that has a branch impedance of Z7, and between this F to E terminal has a branch impedance of Z8. Okay, see, I have indicated the branch impedances. Now I will calculate the Z1, Z2, Z3 up to Z8 using the value of resistor, inductor and capacitors. After that I will replace the branches with their equivalent branch impedances. Okay, Z1 is the branch impedance which contains the resistor of 20 ohm and the inductor of 1 Henry between A and C terminals. So how do we calculate the branch impedance Z1? It will be equal to R plus JXL or R plus J omega L. Here R is equal to 20 ohm, omega is 10 and L is 1. So here I will get Z1 equal to 20 plus J 10. Now see, Z2 is the branch impedance between this C2 D terminal. So here we have a resistor of 30 ohm and a capacitance of 2 millifarad. So our Z2 impedance Z2 will be equal to R minus JXC or R minus J into 1 by omega C. Here R is equal to 30 minus J into 10 into 2 into 10 to the power minus 3. This will be equal to 30 minus J 50. Now see, the branch between this C and D terminal has an impedance of Z3 and it contains an inductor of 2 Henry. Therefore, the branch impedance Z3 we calculate it by using this formula JXL, because it has only inductor. So it will be J omega L. Here omega is 10 and L is equal to 20. Sorry, L is equal to 2. So here I will get J 20 ohm. Okay. Now see the branch between C and F terminal which contains the resistance of 10 ohm. It has a branch impedance of Z4. Z4 will be equal to 10 plus J0 because there is no reactive component. So our Z4 branch impedance will be 10 plus J0. Z5 will be equal to, it is capacitor, so it will be minus JXC or minus J into 1 by omega C. Now look here, minus J into omega is equal to 10. And the capacitance has a value of 5 millifarad, so it will be 5 into 10 to the power minus 3. 1 divided by 10 into 5 into 10 to the power minus 3. This will be equal to minus J 20 ohm. Okay. Now look at C and E terminals. I have this branch impedance Z6 and the branch is composed of 40 ohm resistor, 5 Henry inductor and 20 millifarad capacitor. So in this branch I have the resistor, inductor and capacitor in series. So whenever we have a branch in which R, L and C are in series, we calculate the total impedance of that branch using this formula. R plus J XL or omega L minus XC or 1 by omega C. Okay, see here R will be equal to 40 plus J omega is equal to 10 into 5 minus 1 by 10 into 20 millifarad. Okay, this will give us a value of 40 plus J 45 ohm. Okay, now look between D and E terminals. You will see I have the inductor of 3 Henry and the capacitance of 10 millifarad. So how do we calculate the Z7? See, there is no resistance, therefore real part will be 0 plus J XL minus XC. Now see, XL is equal to omega L, 0 plus J omega L minus 1 by omega C, 0 plus J 10 into 3 minus 1 by 10 into 10 into 10 to the power minus 3. This will be equal to J 20 ohm. Okay. Now look at the branch between F and E terminals. You will see this will have a resistance of 50 ohm. Okay, there is no inductor or capacitor, therefore imaginary part of the impedance will be 0 and Z8 will be equal to, what will be the value of Z8? Simple, 50 plus J 0. Okay, now see, I have Z1 between A and C terminals, I have Z2 between B and D terminals, I have Z3 between C and D terminals, I have Z4 and Z5 between C and F terminals, I have Z6 between C and E terminals, I have Z7 between D and E terminals, and I have Z8 between F and E terminals. Now see, I will replace all the elements with the corresponding impedance block, and that will give us the block diagram of this circuit. See, I have replaced all the branches with corresponding impedances. Z1 was equal to 20 plus J10, Z2 was equal to 30 minus J50, Z3 was equal to J20, Z4 was equal to 10 plus J0, Z5 was equal to minus J20, Z6 was equal to 40 plus J45, Z7 was equal to J20, and Z8 was equal to 50 plus J0. Okay, now I will simplify this circuit. Now look at between C and F terminals. You will see between this C and F terminals I will have the impedance Z4 and Z5. They are connected in parallel. So when Z4 and Z5 will be connected in parallel, I can replace these two impedances with their equivalent impedance. Let's say that equivalent impedance will be Z9. So our Z9 will be equal to Z4 into Z5 divided by Z4 plus Z5, and that will be equal to 8 minus J4. So that will give us the first simplification of the circuit. I will replace Z4 and Z5, these two branch impedances, with a single branch impedance of 8 minus J4. So this will be our first simplified circuit. See, I have replaced Z4 and Z5, their parallel impedance with their equivalent impedance of 8 minus J4. Now look at terminal C and terminal E. You will see within these two terminals I have the Z9, impedance Z9 and the impedance Z8. They are connected in series. So when two impedances are connected in series, I can replace them with their equivalent impedance. Let's say that is Z10. Here Z10 will be the sum of Z8 and Z9. So I will get 8 minus J4 plus 50 plus J0. That indicates that I can replace Z9 and Z10 with an impedance of 58 minus J4. And see, this is our first simplified circuit, and that will give us the second simplified circuit of the given circuit. So this is our second simplified circuit. Now between C and E terminals, see, I have this Z10, 58 minus J4 ohm. Okay, now look between C and E terminals, you will see we have this Z6 that will be in parallel with this Z10. Therefore I can replace them with their equivalent impedance. Let's say their equivalent impedance will be Z11, and that will be the equivalent parallel impedance of Z6 and Z10. So that will be equal to Z6 into Z10 divided by Z6 plus Z10. That will be equal to 30.6 plus J 12.2. Okay, so between this C and E terminals I will replace Z6 and Z10 with an impedance of 30.6 plus J 12.2, and that will give us the third simplification of the original circuit. Okay, see, this is our third simplified circuit. This is our Z11 between C and E terminals. Now look at terminal C and terminal D. I have the impedance Z7 and Z11. They are connected in series, so I can replace them with their equivalent impedance Z12. For example, Z12 will be equivalent series of Z7 and Z11. That will be equal to 30.6 plus J 32.2 ohm. Okay, so between the C and D terminals I will replace Z11 and Z7 with Z12. That will be our fourth simplified circuit. See, this is our fourth simplified circuit, and this is our C terminal and this is our D terminal. Between the C and D terminals I have this Z3 and Z12, and see, they are connected in parallel. So if I replace these two impedances with their equivalent impedance, I will get Z13, which will be the equivalent parallel impedance of Z3 and Z12, and that will be equal to Z3 into Z12 divided by Z3 plus Z12. That will be equal to 3.35 plus J 14.3. So I will replace these two impedances with Z13. And see, this is our final simplified circuit. I have replaced those two impedances between C and D terminals with Z13. And see, look at between terminal A and B. With respect to terminal A and B, I will have the impedance Z1, Z13 and Z2. They are connected in series, so their equivalent impedance or total impedance will be the sum of Z1, Z13 and Z2. So our total impedance of the circuit will be Z1 plus Z13 plus Z2, which will be equal to 20 plus J10 plus 3.35 plus J 14.3 plus 30 minus J50, which will give us a value of 53.35 minus J 25.7, and this is the total impedance or equivalent impedance of the given circuit. Starting of this video, I have told you that equivalent impedance will replace the entire network with some components, and see here we have reduced the total impedance or equivalent impedance equal to 53.35 minus J 25.7, but you have to remember that we represent the impedance Z with resistor, inductor and capacitor. Therefore, you have to understand that how do we represent the impedance ZT with the given parameter. See, here we have 53.35 minus J 25.7 ohm, and if you remember the formula of impedance, you will see I can compare this impedance equation with this formula, R minus J XC, where R will indicate the real part of this total impedance. That means R is the resistance of the equivalent impedance, and C minus JXC. XC will represent the capacitive reactance of the total impedance, XC, which is equal to 25.7 ohm. Here XC is equal to 1 by omega C. Omega is equal to 10. If I put the value of omega here, I will get C equal to 3.9 millifarad, and this indicates that I can represent the entire network with a resistance of 53.95 ohm and a capacitance of 3.9 millifarad. So this is our equivalent impedance, and we can replace the entire network with a resistance of value 53.95 and capacitance of 3.9 millifarad in series. That's it. Thank you.